So yeah, gonna do some engineer. Bro, I'm so cringe. Fuck. I'm so cringe. It is what it is. I'm gonna fuck all you up. That's how it goes, right? I'm gonna do audio engineering. So this is something that I need to look into.
Developers face numerous challenges when it comes to building applications that use
Motherfucker looks
large
like a
language
hamster.
models
What
or
the fuck?
LLMs. In particular, the scarcity of GPUs, which are traditionally required for running LLMs, poses a significant hurdle. Google Cloud is introducing tools and methods to run large language models locally within their cloud workstation environments without needing GPUs. So this makes AI development more accessible and cost effective. Today, we'll be looking at Local LLM, which is a tool developed by Google, and how you can use CPU and memory instead of GPUs. So before we get into the video, a few of the key benefits are there are no GPU bottlenecks, so developers can build powerful AI-driven applications without the common obstacle of needing graphics card. There's improved development efficiency, so local development streamlines the process, letting you avoid managing remote servers or external services. Third, reduced costs. So since you don't need to pay for expensive GPU, whether locally or for remote instances in the cloud, development cost decreases significantly. And last is the enhanced security. So keeping your models and data local can improve security compared to sharing them with external services. So let's look at Local LLM. So this is an article from Google Cloud dated February 6, 2024. I know this is almost end of April, but I finally was able to test Local LLM out, so that's why the video is out now, and I wanted to increase awareness, if you don't have GPUs yourself, or if you want to use Google Cloud workstations. So you can see the title of the article is No GPU, No problem. Local LLM lets you develop Gen AI apps on local CPUs. So I'll link the blog or the article link in the description. So if you want to use cloud workstations, you can go.
That's a question for YouTube. I'm gonna elbow some people.
You can run AI models like ChatGPT on your laptop, all local, no internet required. It's called Olama and it's amazing. To get started, go out to olama.ai. Choose your platform, Mac, Linux, or Windows, and install it in seconds. Now let's launch a terminal and download your first AI model with this command. Olama, cool, and then the model. We'll try Llama 2. Take a little coffee break, and then it's done. To start chatting, type in Olama run Llama 2. And boom, AI on your laptop. Ask it anything. And you can get even crazier. You can set up a beautiful chat interface, add image generation, and custom AI models. We cover how to do all that in this video here. So check it out and tell your friends that you can run AI models like ChatGPT on your laptop, all local, no internet required. It's called Olama and it's amazing. To get started, go out to Olama.
You can now use ChatGPT for literally free. OpenAI just released 2 open source models as powerful as GPT-4, but 100% free. The 20B model runs on just 16GB of RAM, meaning ChatGPT level AI on your laptop. The 120B model matches GPT-4's performance and runs locally on a single high-end GPU. Just comment the word "show me" if you want me to create a detailed video showing how you can install it.
What even is the point if you're not gonna like say it in the shot in itself? You want me to like show me, daddy? You know what I mean? Like the fuck? You fucking retarded.
Last year, we thought 2024 was going to be a job market hell, but it turns out that not only we have even more hiring freeze, we also found ourselves even deeper into the subscription nightmare that is AI services. Because for just $20 a month, you would get your own green junior that is good at coding but bumbles at the same time and can write you some good emails that could have been only 10 words. Some may say that it's money well spent, but some may say that you are not min-maxing enough. Because if I could run free chatbots near equivalent to ChatGPT myself, why would I pay $20 a month for a service just to tell me I can only use it again at 8 p.m.? So if you ever want to know how to run AI chatbots and LLM models locally, this video is the perfect gateway for you. To get started, picking the right user interface for yourself is very important as it'll be catering to your needs depending on how deep you are in the rabbit hole. First, we have text generation web UI and it usually goes by the name Uba Booga. It offers 3 modes: default, which is basic input output, chat, which is like a dialogue format, and notebook, which is pretty much like text completion. It is the current most popular UI and offers most of the basic stuff you need. Second, we have Silly Carvern, which focuses more on the front-end experience of using AI chatbot like chatting, role-playing, and even more visual novel like presentation. But it's just generally a really nice looking front-end for using LLMs, and since it's only a front-end, it will need a back-end like Ooba Booga to run the AI models. But if you just want some straightforward exe file, then there is LM Studio, which has lots of great native functions like Hugging Face Model Browser, which makes finding models much more easier. Other than that, it has some much nicer quality of life info that would tell you if you can run a model or not. It's definitely a good alternative if you don't.
Hmm. I need to reach out to some people. I don't want to dox anyone. I think I've doxed enough people.
So, do you face lags in your computer? Or sure, I do. You do, right? So, what's the spec of your computer? I get.
Why does Y Combinator logo look so lame?
Cloud computing has always been marketed as a solution that claims to save a lot of money. But if you have ever checked an AWS bill, you'll understand that how big of a lie it is. There are idle costs, hidden costs, you are paying for services that you accidentally opted in for, and tons of things like this. That's why teams spend hours every single week configuring the cloud infra so that they don't end up overspending. And this is a serious hindrance in the momentum of any team. On the contrary, I personally have seen startup founders paying more on cloud infra than paying real people, and they hate it. That's why we built Infinity. Firstly, you need zero technical knowledge to access Infinity, and you just pay for the applications that you use. Very transparent. You just log into your Infinity portal, you click on the application you want to use, and you just pay for the exact amount of minutes that you have used that application. As simple as that. You know, it's not about saving pennies actually, it's about trusting the system again. And cloud started with the promise of freedom, but nobody actually delivered it to everybody. We are fighting to deliver it, and we are launching Q1 next year, and you can run anything on everything with Infinity. Cloud computing has always been marketed as a solution that claims to save a lot of money. But if you have ever checked an AWS bill, you'll understand that how
I know what I need to do. The downgrade is insane. The downgrade that some of these bitches go through is insane. They be hard and like, you know what I mean, cute when they're like 18. When the clock ticks 27, it's like it's all goes down. Apparently it's like, statistically it's like 50-50. Why am I not? Okay, I'm done doxing people. I can go back to being a regular incel. Incel a lot. Okay, let's read into this. It's an open source sequence model kit tool developed by Meta AI, formerly Facebook AI Research. It is built on PyTorch and designed to train evaluating neural network models for a wide range of NLP. NLP.
With the previous video, link will be below as well.
NLP, natural language processing. Brother, who gives a fuck, brother? Brother, who gives a fuck, brother? You smash everybody, brother. 10 books to get high. Praying that I don't die. Routing an LLM, building an AI powered app.
If you're building an app powered by AI, you need to know how to use routing within your workflows. Today, we're going to talk about LLM routing and how it differs from classic routing.
Bro, front end, low key. Who the fuck cares? Low key, who cares? Front end. Front end development, who the fuck cares? I know it's like cool and all, but it's like low key, who cares?
My biggest mistake the last 2 months was starting projects, getting excited about the next project, but then not finishing any of them. Today, I did finish one. I finished reading AI engineering and making the mind map that I've been building of it. It feels really good to finish a project. What have you been procrastinating on that you can finish today? Drop a comment and then enjoy the music. Today, I did finish one. I finished reading AI engineering and making my map of the concepts. It feels really good to have something completed.
Bro, where is your mind map? Where can I get it? I want to see your mind map. Why does it look retarded? Bro, the fuck is this website? Don't give a fuck, nigga. Just... How much do you like? wires, bro. I just wanna crush your skull. Fuck. I don't give a fuck about your physics thing, man. Respectfully. Respectfully, where is the mind map? Brother, respectfully. Okay. Thank you. What? Use the arrow. What the fuck? My Twitter is low-key racist. What the? Where's my message, bro? Or does he not? It's probably on his head now. Fuck. Let's take a look at it. Fuck. Why am I should be doing something else, but fuck it. I'm gonna get back to it though. Mind map. Three low. Marketing slop. AI versus ML engineers typically involved a lot of data and a lot of math. It's more about putting systems together that outperforms existing model. Well defined. ML engineering typically involves a lot of data, a lot of math, training your own models and performing well-defined tasks such as classification. Okay, I'm doing ML engineering then. AI is more about putting systems together that outperforms existing models. Okay. I don't want to do AI engineering. I want to do ML engineering. Different. It's different level, bro. It's different level. Wally. Neural. First I need to like start with this though. Apparently. Introduction. Fastwork is a sequence modeling toolkit. What does that mean? I need to understand every single sentence that I'm looking at. You better give me like some sort of.
One of the challenges of machine translation is that given a French sentence, there could be multiple English. Hello and welcome to this final week of this course, as well as to the final week of this sequence of 5 courses in the deep learning specialization. We're nearly at the finish line. In this week, you hear about sequence-to-sequence models, which are useful for everything from machine translation to speech recognition. Let's start with the basic models, and then later this week, you hear about beam search, the attention model, and we'll wrap up the discussion of models of audio data like speech. Let's get started. Let's say you want to input a French sentence like Jean recycle l'Afrique in September, and you want to translate it to the English sentence Jane is visiting Africa in September. As usual, let's use x1 through x, in this case 5, to represent the words in the input sequence, and we'll use y1 through y6 to represent the words in the output sequence. So how can you train a neural network to input the sequence x and output the sequence y? Well, here's something you could do, and the ideas I'm about to present are mainly from these 2 papers due to Ilya-Suskova, Olya Daniels, and Quackler, and that one.
It's moved on so fast. The whole thing has moved on so fast. Andrew NG. Okay, bro, so many noise. This is outdated. Let's look into it. It's a sequence modeling toolkit that allows researchers and developers to train custom models for translation, summarization, language modeling, and other text generation tasks. It provides reference for implementation. How does it actually models including I need to like there's so much shit to write. This should go here. We have CNN convolutional neural networks and light conv and dynamic con. Bro, that's like crazy. When people long short term memory, LS long short term memory. Transformers. That's another one. FastSec feature. The multi-GPU distributed and on one machine across multiple machine. Fast generation on both CPU and GPU with multiple search algorithm implemented. Beam search, diverse beam search. Vijay Kumar. Okay, sampling unconstrained on top of K. Large mini batch training even on single GPU without delayed updates. Mixed precision training trains faster with less GPU memory on NVIDIA Tensor. Okay, extensible easy register new models criterion task optimizers and learning rates. We also provide this thing translation and language model data set requirements and installation. And you did on the PyTorch. I have it. Okay. Instruction. If you use Docker, make sure to shared memory size with either IPC host. Okay. And command on NVIDIA Docker run. After PyTorch is involved, you can use with pip. Okay. I think I installed PyTorch. to install FastTag from locally developed get clone. Oh, I think I have it. Training improvement and training speed. Training speed can be further improved by NVIDIA's Apex library with okay, getting started. Full documentation. Interesting. In this tutorial, we will extend by adding fast decoder model that encodes the source sentence with LSTM and passes the final hidden state to the second LSTM that decodes the target sentence without attention. Okay, writing this is what we did like a couple of hours ago, so should be fun. Registering new models so that can be used to create command line tools. Okay, training the models using the existing command line tools, making generation fast by modifying decoder. Okay, building an encoder and decoder. In this section, we will define simply LSTO encoder decoder. All encoders should be implemented. Fast square encoder interface and decoder should be implemented with this thing. These interfaces themselves extend this. Okay, so FastSwitch encoder and FastSwitch decoder can be written and used in the same way as PyTorch models. Encoders. Our encoders will be embedded the tokens in source sentence, feed them to torch this thing, and return the final hidden state to create encoders and save the file name. Okay, torch neural network, FastSwitch util. Okay, it's like a big ass encoder. Our decoder will predict the next word. Okay, what is going on? I should read into it, right? A simple LSTM encoder. Forward in it. Making generation faster. Okay. LSTM. Bro, this is like low key. What the fuck am I looking at? The sequence to LSTM. Okay, whatever. Let's see.
We got a legendary sequel equivalent to Top Gun Maverick in machine learning a few.
This nigga is basically biting his whole style. Like, what the fuck? LLM attention. But the interesting thing is, so who the fuck is this guy? I need to follow these people. Following. I need to follow these nerds, man. In actuality, who the fuck are you? Who are you? I wanna see who the fuck are you, man. Dame, dame, man, you remember 5 years ago? Crazy. That shit is crazy, bro. 5 years ago. Who is this guy? Like, who the fuck are you? You just like read research papers all day? Yeah, definitely. So easy. Okay. I'm supposed to. I know what I need to do. I might be able to get an internship. Lucky. Fuck. Shit, I'm just like putting my business out. Oh, can you like not? Can you like close this? I don't want. Fuck's sake. Very first open source training framework for public use. It contains many code patterns. It'll make you read other repos much easier. In terms of language models, that's for coding, hacking models, for concepts, the 3 papers that I mentioned above. Ooh, I think I can like do some shit with it. Let's go here. Crazy synchronicities going on. It's gonna take some time. Estimated 2 minutes. Fucking kidding me. Strained on. Nah, don't do that. Fuck. Okay, let's just look at the slop.
Few days ago, and the machine learning scholars sure are eating good these past few weeks. While the first one, Ken, was kind of bold in aiming to replace MLP, this time, however, we have a good old trusty tool in the shed getting upgraded from LSTM to a new and mighty XLSTM, short for Extended Long Short-Term Memory. It is also written by the same author, Sepp, who has also been shilling XLSTM ever since February, which you can find some clues here and there on various sources mentioning how he claimed that XLSTM is better than Mamba, with absolutely nothing to back it up during the time when Mamba was rising to fame. But now, as the XLSTM paper has been published, we can finally see what saw in his XLSTM experiments and know if he's high on copium or not. What's interesting about XLSTM is that it technically proposed two different LSTM architectures, one's called Scalar LSTM and the other is called Matrix LSTM. Then they can be optionally joined together to create an XLSTM block. But why two architectures? Well, due to the nature of LSTMs, the problems cannot be simply solved with just one architecture, and some sort of trade-off has to be picked. Something that's really unique to RNN, or more specifically LSTM, is that each hidden block relies on the output of a previous hidden block. This is called memory mixing, and it is incredibly inefficient due to the need for sequential processing. So while transformers can quickly get the entire output with a matrix multiplication, LSTM would have to calculate the output of the individual hidden states sequentially, which makes LSTM slow to a point where it is pretty much unscalable. So to overcome this, MLSTM abandoned memory mixing and instead picked up something called matrix memory, which made LSTMs parallelizable. By also sprinkling exponential gating on top, this solved the old LSTM problem where it'll struggle to revisit a stored value when a more similar vector is found. With how MLSTM is designed, its residual block can then be structured similarly to state space models. On the other hand, abandoning memory mixing might be a waste, as it is also LSTM's key strength that made it stand out in the first place. Even though it does fail miserably sometimes when trying to revisit values, LSTM was still peak until Transformer was introduced. It was pretty much the best architecture in reinforcement learning back in the days, like the Alpha Star model for StarCraft 2 and OpenAI's Dota 2 AI that beat the best professional teams back in 2019 are all built upon LSTM. It excels perfectly at learning abstractions like semantic information, and it was good, like how it fixed the vanishing gradient problem that RNN had by using constant error carousel and gating, but it wasn't perfect due to the drawbacks I mentioned earlier. So as LSTM incorporates the exponential gating that MLSTM also has, and consequently created a new memory mixing technique to improve the Alzheimer's that LSTM had, and its residual block had to be arranged in a similar fashion to transformers, which looked like this. While using SLSTM would also mean that it is not parallelizable, it still, well, hopefully inherits the strong learning capacities and attributes that we will see later in the benchmarks. As you can see here, for these labels, 0 to 1 uses only SLSTM, 1 to 0 uses only MLSTM, and 1 to 1 has a 1-to-1 ratio of SLSTM and MLSTM. So by using a different mix of each component, the researchers further tested different types of combination and see how it affects its performance. Then it is compared to other popular architectures like transformers in Llama, state space model in Mamba, RWKV, which is also RNN inspired architecture, Hyena, retention, and the original LSTM. And by a pretty decent margin, XLSTM and LSTM both outperforms all others across the board, with the most success on the mod arithmetic benchmarks, as it is in operation only LSTM models are able to learn. So you can see transformers or other methods failed miserably here. On the other hand, it is interesting to see that XLSTM with only MLSTM performs subpar than other XLSTM structures, as MLSTM is also the one that removed LSTM's key attribute, which is memory mixing. It also failed the mod arithmetic benchmark, which is an interesting observation for sure. The most interesting takeaway from this though is that from these toy benchmarks, the classic LSTM still outperforms most of the other architectures. However, later you will see it fails to scale up. But yes, LSTM is actually good to an extent. So after running through the toy benchmark,
What is going on? That's his famous video? Oh, that's kind of his famous video, isn't it? Who the fuck is him?
Hey guys, it's me, Cloud, or officially known as ByteCloud. And by the time that this video is live, hopefully I have 200,000 subscribers. But if not, well, that's just another excuse for my face reveal. But the main update I want to give you guys today is that I am taking a tiny hiatus. Well, you guys probably wouldn't feel anything because I am pretty not up to date. But the point is, I am going to the military. And you know what that means? I have to shave my head. So, after some careful PR decisions, I decided that it's such a great idea to face reveal and shave my head at the same time. Well, of course, that's not the entire reason. I feel like I want to do different kinds of content and potentially blend some real life elements into it. At the same time, I also want to improve my public speaking skills, because one of the key reasons why I started doing YouTube is to practice my English fluency. Like, can you imagine this is how I sound like 5 years ago?
And this product is called Price Aggregator, and it's written in Python, and it uses WebDriver, Selenium WebDriver library, and Pygame, and HTML writing.
So thank you for supporting me in the past 5 years. As for the main subject, since I am Taiwanese, I have mandatory military service. But luckily for me, I only need to do it for 4 months. As for people younger than me, they have to do it for a year. So it's a pretty short hiatus, and it'll feel even shorter. Luckily for me, I only need to do it for 4 months. As for people younger than me, they have to do it for a year. So it's a pretty short hiatus, and it'll feel even shorter because I have a backlog of videos that I'll post here and there. The only unfortunate part is that I will no longer be as up to date on the research side of things anymore. But I promise I'll be right back on track after catching up 4 years worth of AI progress during these 4 months. Anyways, let's cut the chase and cut some hairs.
Fucking
But
pussy.
you know what I won't miss out on? My BuyCloud hat down in the store.buycloud.ai, and I'll see you guys in the next time. And cut some hairs. Longer be as up to date on the research. But luckily for me, I only need to do it for 4 months. As for people younger than me, they have to do it for a year. So
Okay. Man, should I even like
weird text to speech AI?
should I even like be an AI researcher? Who even how do I like market myself as a AI researcher? fuck! No, new chat. Okay, those three things. I'm gonna.
text and
fuck's sake, I have Telegram. What the fuck? I need to like yap about things. Yap, yap, yappity yap. So much yapping to be done. I need to yap max. Yap, 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 yap. I need to max out the yapping skill. Nothing else. I need to message these guys on internships. Ooh. Applications, solution, test task, 13 interviews. Fuck no. I mean, yeah, 13 interviews seems alright. Oh fuck. Oh, it's just you just have to like sit and like Bro, you're just looking like you're jerking off. What the fuck you doing? Conclusion. In summary, the provided research paper do not contain information called framework called valid. However, they are confident. Bro, what do you mean? It's right here in front of me. What the fuck are you talking? Based on, however, the provided research paper essentially on content broader topic on neural concept generation, detailing the detailed context on neural concept frameworks. According to the research paper that I found on basic search, the neural refers to the use of deep learning models to compress audio signals into compact, discrete representation tokens, and then generate high fidelity audio from these tokens. The process is central approach to modern AI pipeline for audio generation understanding. How do I? This one? That one does nothing. How do I like see the paper? Who's this guy? Everyone here is like PhD. That's view PDF. Okay, scaling for low bitrate, high quality speech coding. Julian D. Parker. Who are these people? Are these our PhDs? Abstract. The tokenization of speech with neural audio codec model is a vital part of modern AI pipeline. Let's look at AI pipeline. Fuck. Too much. Shut the fuck up, bro. Fucking idiots. Traditionally, such tokenization models has concentrated on low parameters count architecture using only components with strong inductive biases. In this work, we will show by scaling transformers in architecture on large parameters count to the problem applying flexible, finite quantization based bottlenecks. It is possible to reach state of the art quality extremely low bit rates, okay, per second. What is even a bitrate? Trained models strongly outperform existing baseline in both objectively and subjective test. Introduction. Compressed coding or audio speech data in a digital format has been an actively since 80s. Research particularly predominant in with emergence of MP3 printers, standards. Research into improving the sound quality and compression radio of such codecs, mainly used in signal processing techniques, has continued The main purpose of these codecs is to improve the efficiency of transmission, the storage of what it is traditionally. Okay. In recent times, the research community has begun to apply techniques of machine learning to the audio coding problem. These models are referred to as neural audio codecs. Let's look at this. Mm-hmm. Minimized audio quantity. However, a paradigm shift occurred in the postal powerful generative model quantization token sequence produced by the codecs. Okay. With arrival of these models, the phenomenal plethora of use cases encompasses the design of NAPC. They has shifted to less concerned with computation complexity and more concerned with pushing compression, especially in the Our goal is to design speech codecs model in the spirit of the paradigm shift, whose primary purpose is in the combination of model generative architecture for generation of understanding of speech signals. We make the observation in the typical modern generation pipeline for speech may be a model of billion parameters, tiny fraction, which is usually dedicated to codecs model. There is therefore some headroom to increase the size of component without overly impacting the overall computation burden. This opens up scaling the codecs model size as route to higher quality audio and higher compression levels. Neural audio codecs model have largely been based on convolutional or recurrent architecture, which can it's a convolutional meaning convolution neural network. That's what I've been working with, which can be challenging to scale larger model size without placing restriction on the architecture. Even with such restriction, the largest successful purely convolutional networks are generally below 1B parameter. Oh fuck, don't do that. Stability.ai. Showing ability to scale billions of parameters in many domains, but have not been fully utilized in codecs yet. Recent work have also had deployed transformer block in the bottleneck of convolution codecs, showing the improvement in compression ratio. However, the transformers has not yet been deployed as many components of codecs model. One of the major contribution of this work is to design new codecs architecture that are predominantly transformer based. The scale of such architecture into 1 billion parameter, and the majority of the current codecs utilizes this is the thing that they're doing, scaling transformer follow. And what are we using currently? I think we're using RVG in some form. This is effectively maximizing the expressive of bottleneck for given bit rate, but the present number challenge as generative model. One challenge is to produce many parallel hierarchical stream of token. The causal relationship between streams introduces a variety of complication that must be accounted for during training and interface. An additional challenge in VQs and RVQs can suffer poor inconsistent code books utilization, making the process learning and token contribution more difficult and prone to bias. In this work, we will address the VQs. What is VQ and RVQ? Got it. What is VQ? What is VQ and RVQ? That's good. In this work, we will address the issues of VQ and RVQ instead of adopting the quantization scheme derived from finite scalar quantity. scalar quantity. I like titties. As a novel post hoc method, decomposing into lower order residuals, we demonstrate how the contribution enabled training of waveform codex model that is achieves high compression for speech with ultra low bit rates, okay, while still preserving good audio quality. Okay, I need to look into this. Fuck you. Why? Why are you such a fag? Okay, related work. Can I introduction, related work, architecture, okay, discrete bottleneck, post-training bottleneck modification. Yeah, some fucking math. Experiments. Okay. Limitations, conclusions, reference. This is all reference, appendix. Oh. Neural audio codecs. The dominant paradigm of NAC has been far in VQ and VAQ structures. VAQ structures. I think I need to like look into this. I need to look into like so much things at one specific instance that it almost becomes like what am I doing? You know? So much shit to like look into. Vector. Oh, what is this? $17. Wow. Generative AI animation. Fuck, could you like say it like really fast?
The primary goal of representation learning is to produce some efficient representation of the underlying data. Now this representation can be continuous, as in a variational autoencoder, or it could be discrete. And in fact, when we use language to express
Vector quantized variance autoencoders.
image, we're actually distilling a continuous representation into a discrete form. This is the basic motivation behind the vector quantized variational autoencoder, or VQ-VAE, which is basically a variant of the VAE in which the latent representation is discretized or quantized. So instead of having an infinite number of possible latent vectors, we now have to choose from a limited collection, which is known as our corpus. Now this clearly constrains our latent representation, so why would we do this?
Who is this dude?
Explore why we might want to quantize, and how the VQ-VAE achieves this. We'll do this by first refreshing ourselves on the regular VAE, then seeing how the VQ-VAE modifies this basic scheme, and finally we'll talk about some of the benefits of quantization. So the VAE is basically a probabilistic latent variable model that encodes a data point to a distribution in latent space, and also decodes a point in latent space to a distribution in data space. The idea here is that we have some target distribution in data space, say the distribution of chairs, and we want to map this to a specified prior distribution in latent space. The idea being that if we then sample from a prior distribution in latent space, we're going to get some chairs in data space. So, when we put some data point x into a model, the corresponding latent vector z is sampled from a Gaussian distribution whose parameters are defined by the encoder. The sampling is controlled by a stochastic variable eta. Then finally, our reconstruction y is produced using the decoder. Now the model as a whole is trained using a two-part loss function. The first part is a reconstruction loss that rewards the decoder based on the log likelihood of the original data. Then we have a distribution or KL divergence loss that penalizes the divergence of the posterior latent distributions from our pre-specified prior distribution. So we basically have four essential elements here.
we have a continuous latent encoding, a Gaussian sampling procedure in the latent space, a pre-specified latent prior distribution, and a loss function that penalizes on reconstruction and KL divergence. Now we're going to see how the VQVAE modifies all four. The first important element is the discrete latent encoding. So let's take a look at how this works. So our model as a whole has three trainable components, the encoder, the decoder, and the codebook. The codebook is defined by two hyperparameters, the dimension of the latent space d, and the number of latent vectors or code words k. So in the forward pass, our input x is first fed through our encoder. For example, we may have some red, green, blue image, which is 128 pixels wide, 128 pixels tall, and 3 channels deep. If our encoder is a conventional neural network, then this may condense our image to a feature representation which could be, say, 4 pixels wide, 4 pixels tall, and 16 channels deep. So we essentially have 4x4, 16-dimensional feature vectors, which we treat as our encoding latent vectors, CE. This also means that our codebook dimension d is equal to 16. So now we've reached the quantization step. Here, each encoding latent CE gets replaced by the closest code word in the codebook. So this code word then becomes our quantized latent ZQ. And here, closeness is just measured using L2 norm, or Euclidean distance. So basically, each encoding vector ZE snaps onto the closest code word in the codebook to become the quantized vector ZQ. So every latent that's fed to the decoder has to be part of the codebook. Okay, so now the final step is just to pass our quantized latent to the decoder network, which simply outputs our reconstruction of 1. So now we've already established one key difference with the regular VAE. While the VAE uses continuous codes, the VQ-VAE uses a discrete codebook with a nearest neighbor lookup during the forward pass. Now you may have noticed that during the forward pass there is in fact no random sampling, and that's correct. Unlike in the regular VAE, the forward pass of the VQ-VAE is completely deterministic. This is a second major difference. But how can we square this deterministic picture with the probabilistic modeling framework of the VAE? Well, recall that in a VAE we have a predefined prior, and we're essentially trying to match the target distribution data space with this prior latent space. As such, the prior essentially biases the latent posteriors due to the presence of our KL divergence term. Our prior and posteriors are all Gaussians, so the only way to bring the KL divergence term to 0 is to make our posteriors all have a mean of 0 and a variance of 1, which means that they're equal to the prior. Now the VQ-VAE picture is a little different. Instead of using a Gaussian distribution as a prior and posterior, we instead have a categorical distribution. And this is simply the probability of choosing any particular code word index k. Now of course the nearest neighbor lookup procedure is deterministic. For posterior, the probability of 1 for the nearest neighbor index and 0 elsewhere. But what about our prior? Well, during training we actually do not wish to bias our model in the code word indices or choose. So our prior is just a uniform categorical distribution, with each index having probability 1 over big K, which is our codebook size. Right, so given this prior and posterior, it's now possible to calculate our KL divergence. First, we take our KL divergence formula for discrete variables, then we apply this over all codes in the K. Now the posterior is 0 for all but the nearest neighbor, and for this is equal to 1. So we can write this as simply log 1 over big K, or just log big K. So basically our KL divergence is a constant that just depends on the codebook size big K. As such, it never features in our training objective. Now here we should note that even though we don't wish to bias the code word selection during training, we may notice after the model is trained that the joint distribution of code words across our dataset is not a uniform distribution. So for example, in our dataset of chairs, we may notice that having one code word in location 1 might prejudice or condition the distribution of possible code words in location 2, and so on, such that if we straighten this distribution, we'll end up with something other than a chair. So even though our prior is kept fixed and uniform during training, in some sense there is a true prior that reflects the distribution of chairs, and this is actually learnt during training, and does not necessarily have to be equal to the uniform prior we had before. This kind of conditionality is also very apparent in domains such as language modeling, where subsequent code words should clearly depend on previous code words. Now this is clearly different to our VAE framework. In the VAE, the prior is predefined and fixed, while as we mentioned in the VQ-VAE, we have a true prior that is learnt during training. However, there's one difficulty with this scheme, and that is even though our model has implicitly learned some kind of true prior, we don't actually know what it is. So the authors of the VQ-VAE paper propose using a secondary model, an autoregressive model, to learn the appropriate probability distribution of the code words. Now the basic idea is that we should incrementally build our code word selection via ancestral sampling. This just means that we sample one variable first, then sample the rest consecutively from distributions conditioned on the previous or ancestor variables. So say we want to sample some image from the learned prior. What we would do is first generate all of our code words by ancestral sampling in a raster scan order until we've selected every code word. And then we just decode as usual. Now of course the question is, how do we learn these conditional distributions using our sampling? And that's where the use of autoregressive models comes in. So for the VQ-VAE paper, the authors use a pixel CNN to learn the prior for images, and they use a wavenet for audio. Now of course, given the discrete token-like nature of the latents, we can use transformers as well. Okay, so now we've seen how the VQ-VAE is unique in the sense that it has a deterministic posterior and also a true prior that has to be learned using secondary autoregressive models. The only thing left to talk about is the loss function, and as it turns out, there is quite a lot to talk about it. So we've already established that there is no KL divergence loss, but we still have a reconstruction loss in the form of this negative log-like figure here. Now the calculation of this loss depends on all three components of the model: the encoder parameterized by phi, the decoder parameterized by theta, and the codebook, which we denote as big C. Now realize that there is no longer an expectation over the posterior, because now the posterior is deterministic. Now the way we would transmit gradients to a neural network is typically through backpropagation, and we could do that just fine for the decoder. But we hit a problem at this quantization step here, and that's because the quantization operation is not differentiable. Therefore we cannot transmit gradients to the encoder and codebook via backpropagation. The very simple solution is to simply copy over the gradients from ZQ to ZE. In other words, the gradient is simply passed straight through the quantization layer, which is why this trick is called straight-through estimation. We're basically estimating the gradient that ZE should get using the gradient of ZQ as an approximation. Now to use this straight-through estimation, it would work best in this context if ZQ were a good approximation of ZE. And this is why it makes sense to use the nearest neighbor lookup as a quantization procedure. However, the flexibility of our encoder and our model as a whole would be severely limited if our codebook vectors had to remain static. And here the problem is that even though straight-through estimation can pass gradients to the encoder, it still doesn't pass any gradients to the codebook, which is randomly initialized at the beginning of training. So in order to optimize the codebook, we have to introduce a second loss term called the codebook loss. And this basically just penalizes each code word vector E based on its square distance from its associated encoding vector ZE. Now note the existence of this stop gradient operator here, and all this basically does is assess the gradient of the thing inside it to 0 during the backward pass. So basically, this loss does not provide any gradient signal to the encoder, even though the encodings are required for its calculation. As such, it only optimizes the codebook. Now, you might be wondering, what about those code words that never get chosen in the batch, and therefore don't show up in the loss? Well, the quick answer is, nothing happens to them, and they don't get updated at all. So this is this. But left with just this loss function, we may experience some undesirable behaviors during training. The first is when our encoding fluctuates too wildly between different code vectors. This is especially prone to happening if our encoder parameters train more quickly than our codebook. Now, fluctuations are undesirable because they lead to instability during training, and they can also lead to inefficient codebook utilization, which can include some redundancy between code words. Now, the second undesirable behavior is when the encoding vector grows arbitrarily large as training progresses. If this just so happens to improve reconstruction, then we'll be encouraged, and the relevant code word will try to follow along. But very large encodings are undesirable, as they can lead to training instability. Now, the issue is that since the code does not penalize the encoder, the encoding is never encouraged to move itself closer to the code vector. To rectify both these issues, we add a third loss term known as the commitment loss, which basically penalizes the encodings if they stray too far from the selected code words. Now, this loss looks a lot like a codebook loss, except that it updates the encoder instead of the codebook, due to the stop gradient being more difficult. Here is an umpire rate of 128 numbers.
Hello everyone, my name is Bai. I am a machine learning engineer as well as a PhD in natural language processing. And today I'll talk...
Machine learning engineer and a PhD? You fucking kidding me, bro?
about several different types of transformer. Hello everyone, my name is Bai. I am a machine learning engineer as well as a PhD in natural language processing.
Machine learning engineer and a PhD in natural language processing. So this nigga is like a millionaire right now. Isn't that crazy? And it follows GitHub. Follow this nigga. I previously interned, okay, London during I worked closely with this guy at Chinese University of Hong Kong. I graduated with first class honors in Main University of London with a BSc in Tech. Okay, I'm open to research collaboration, please. Bro, can I be a friend? Team leader Stability AI, London, UK. Oh shit, like Can I get into stability AI without a degree? Yo, can I? Okay. This nigga's cracked. I'm doing it because my chigga told me to do it. But other than that, I'm not really like too big into it. I might like I might produce some music if I get really good at it. Who knows? Who knows? Okay. I'm gonna pretend like I understood that video. Understand? Neck place, bottleneck place in between the quantizer and sound stream was the first example in such model aimed at handling varying bit rates and types of audios on a single model. Soundstream introduced on an adversarial loss in addition of reconstructional loss, residual RVQ. What is RVQ? Oh, that's what I'm looking at. Let's look at the thumbnail though. I need the thumbnail. It so looks like doesn't look pretty. I need a pretty thumbnail. I might do this though. From fuck's sake. See? And what is this? like what the flip?
Some efficient representation of the underlying data. Now this representation can be continuous, as in a variational autoencoder, or it could be discrete. And in fact, when we use language to describe something like an image, we're actually distilling a continuous representation into a discrete one. This is the basic motivation behind the vector quantized variational autoencoder, or VQDE.
Ooh. Let's go.
We will be implementing a fully functional text-to-speech system, or a PTS system. The architecture that we're going to be doing here today is the Tacotron 2 architecture.
Brother. Brother, are you fucking kidding me, brother? No, the entire thing. This is like... Yeah, I need to do this. What the fuck?
Hey everyone, today we will be doing our first example for automatic speech recognition, specifically implementing the DeepSpeech 2 architecture. So there are two prerequisites going into this video. The first one is that you're already comfortable or understanding CPC loss, sectionist, and world classification loss. I already have an entire video describing exactly how the algorithm works, so I will link that down below for the part above. And also, you are comfortable or have heard of spectrograms, right? Converting signals to spectrograms. So the spectrograms that we are going to be using to convert our audio to essentially something that looks like a picture of an audio that describes the time frequency information of
Where do you work, Pajit? Fuck, can a nigga just go in? I don't wanna do signing, please. Please, ladies, don't. Let a nigga live, please. I just wanna stalk people. Coventry, yeah. Ah, I just wanna like look at people. Bro, such so ageist. What do you mean like you cannot like work? You know what I mean? Yo. Nah, bro. Wow. I can connect with a lot of people. Fuck off. LinkedIn. Bro, why the fuck did it? The fuck? So weird, bro. Let's see. What do you do? What do you do for a living? Premise. Okay, you're a researcher. associate data scientist, system developers, data scientist intern, junior developer, data scientist. Marketing intern. Nigga, what? Oh, we need to like post more videos. Fucking dork. Do what you do, bro. You do you, son. Me? Oh, almost spilled my water again. Okay, whatever. Such a goat. Goat activities, man.
Hey everyone, so today we are going to be implementing the rest of the transformer model. So as a quick recap, in the first video we did a super deep dive into attention, just to understand all the variants that you see in regular attention, attention with padding masks, we looked at causal attention, and we looked at cross attention. We're going to need to put all of these things together to perform our machine translation task. And in the next video we looked at preparing the data set. So we're going to pick up right off from where we left, but let's just quickly recap again. If we do Python, new hi. Right, this is the data set that we prepared. Basically, as you can see, we have source input IDs. These are going to be our input English, already pre-tokenized, ready to go, because we cleaned that data set, cracked it, and everything last time. So we have our source input IDs, we have corresponding maps, right? Because different sentences are different lengths, so we need to make sure we add a padding mask to not attend to these extra tokens that we add in. Again, if you're a little bit confused about what these padding masks exactly are, then please just go take a look at the previous video. We also need to do, we have our input French, starting with our begin the sentence statement, and we have our output, right, the thing that we want to predict. And basically this is just offset by 1. So with our input goes 2, 6, 8, 4, 2, 2, 6 by 1, and notice our output is 6, 8, 4, 2, 2, 6 by 1, so it's the same thing, just offset by 1, and we have the corresponding mask for our French as well, right, because we have different French sentences or different lengths, so we need to make sure we add them accordingly and ensure we don't actually enter those padding tokens. So now that we have all this, let's go ahead and just begin our implementation. So to implement this model,
Bro, such a goat. I'm gonna.
there's a couple things that we are going to need. So first, we're only going to be using basically.
I'm gonna. I know what I need to do tomorrow. After lead coding. Fuck. Don't do that. Bro, I can spell scratch. What? Whatever. Okay, I'm gonna. Fuck, it's 9 p.m. Okay, I'm gonna do that then. I'm gonna. Don't need it. 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 Yeah, I'm gonna look into this. You can like go in here. Don't need it. Don't need it. Don't need it. Don't need it. Yeah, I'm gonna do this now. I have like 6 projects.
Hey everyone, today we are going to look at inter-audio processing, and more specifically, how we work with audio to train neural networks. We're not going to look at neural networks today, we're mostly going to look at that pre-processing step of how do we get audio ready to actually pass it into a neural architecture. Working with audio is quite a bit different from working with images or text, so that's why I want to make this video. And also, we're going to just look at a high level how to use the word audio package and how the different methods are related to each other.
I want to get this one done today. Whoa. Bro, I'm so cracked. I'm so cracked. Volleyball bitches. I know exactly what I want to do. I know exactly what I want to do.
In future videos, we'll go in and actually look at some of the theory and implement these methods from scratch. So today is mostly just a use case, a practical use case of what's going on.
audio processing for deep learning. I'm gonna get cracked at this. I don't give a fuck. 6 mini projects in 6 days. Don't give a fuck anymore. What do we actually needed? CTC classification, temporal classification, audio speech recognition, paper overview. Let's reproduce. Fuck yeah. Fuck yeah, that's what I'm talking. That's what I'm talking, nigga. It's Quest to Conquer RL. What the fuck is RL?
Hey everyone, today we begin our quest to conquer reinforcement learning. Reinforcement learning is one of the coolest things you can do with neural networks, but what we're going to slowly see is the neural network is the least interesting part of reinforcement learning. And the only way this is going to make sense is if
Hey everyone, so today we will be digging into PyTorch. This is going to be an introduction to get you more or less knowledgeable of all the different things you can do in PyTorch.
Don't need it. Autoencoders.
hey everyone.
Mapping the... What is autoencoders? Bro, why is this stupid reel in here every day? Okay. If you like, that's for coding and hacking models, the concepts for 3 models, okay. Yeah, I'll look into it. Auto. Let's go in here. Autoencoders. March.
Hey everyone, today we are Hey everyone, so today we are going to be taking a look Hey everyone, today we are going to go ahead and start exploring extractive Q&A. So this is basically a follow-up to the Roberta implementation that we did. In our kind of first Roberta video, we just had a general idea of what is mass language modeling. Then we did a full reproduction script of Roberta, and we were able to get results kind of close, but Roberta by itself is just a fancy fill-in-the-blank model. Like, that's all it can do. So what we're more interested is taking a model that understands something.
10 bucks to get high, you pray that I don't die, you burn if I die, see you inside. I'm gonna take a little break and come back. I need to come up with like really good video ideas, man. It's crazy. I need like a stapler. Fuck. Okay, I'm gonna take like a short little break. Fucking hell. I need a stapler. I'm gonna listen to some music. I'll come back.
everyone.
Today we are going to look at intro to audio processing, or more specifically how we work with audio to train neural networks. We're not going to look at neural networks today, we're mostly going to look at that pre-processing step of how do we get audio ready to actually pass it into a neural architecture. Working with audio is quite a bit different from working with images or text, so that's why I want to make this video. And also, we're going to just look at a high level how to use the Torch audio package and how the different methods are related to each other. In future videos, we'll go in and actually look at some of the theory and implement these methods from scratch. So today is mostly just a use case, a practical use case of what's going on. So let's go ahead. Of course, if we're going to be working with audio, we need some audio to work with, so let's do that. NumPy, SNP, import matplotlib.pyplot, SPLT, and this is going to be a lot of copy pasting today because I mostly want to show visuals and y'all don't need to see me write code of making different visuals, but our main goal is to understand the Torch audio package, at least some of the main methods that exist in it, for us to use in the future. So we're going to import Torch audio.
SD. This is just like your torch vision.transforms, but it's for audio. And then import ipython.display. And we're going to do from ipython display import audio. That'll let us actually visualize or play back one of the audio files. And so I already have an audio file in here that I've gone ahead and saved, so we're just going to take a look at that. And so our audio file is going to be for some audio, and it's going to return both the audio and the sampling rate. And that's going to be torch audio.load, and we're going to go ahead and load our sample audio.flac. There we go. So that's going to be our audio file, and the audio file will sound like this. Audio, we want to play back this audio, and the rate is going to be the sampling rate. And it should sound something like
A distinct promise of 100 pounds was made to him if he would have the child ready to hand over.
Right, just some standard speech audio file. So first of all, if you've never heard of this term sampling rate before, the sampling rate is how many samples per second does your microphone capture. Basically, how many numbers are we using to represent the audio. So in this case, if you look at audio is basically just a list of numbers. It's a and it should sound something like
A distinct promise of 100 pounds was made to him.
FLAC files. And so let's go ahead. Of course, if we're going to be working with audio, we need some audio to work with. So let's do that. NumPy SNP import matplotlib.matplot SPLT, and there's gonna be a lot of copy pasting today because I mostly want to show visuals, and y'all don't need to see me write code of making different visuals. But our main goal is to understand the Torch audio package, at least some of the main methods that exist in it, for us to use in the future. So we're going to do import torch audio.transforms SD. This is just like your torch vision.transforms, but it's for audio. And then import ipython.display, and we're going to do from ipython display import audio, and that'll let us actually visualize or play back one of the audio files. And so I already have an audio file in here that I've gone ahead and saved, so we're just going to take a look at that. And so our audio file is going to be first some audio, and it's going to return both the audio and the sampling rate, and that's going to be torch audio.load, and we're going to go ahead and load our sample audio.flac. There you go. So that's going to be our audio file, and the audio file will sound like this. Audio, we want to play back this audio, and the rate is going to be the sample. Sampling rate. And it should sound
What am I facing? What the fuck? Why is it? What the fuck is going on? I'm gonna.
distinct promise of 100.
What the fuck is wrong with that? Payment, come on, bro. Standard student registration. What the?
Hello everyone, my name is Bai. I am a machine learning engineer as well as a PhD in natural language processing. And today I'll talk about several different types of transformer architectures. Now, if you're new to machine learning, you might be overwhelmed by all of the varieties of transformer architectures available out there. But fear not, because really, there are only three types of transformer architectures. That's the encoder-only models, the encoder-decoder models, and the decoder-only models. In this video, I'll explain the differences between these types of models and give examples of what each type of model is good for and when you should use it. And hopefully you will get a better understanding of these type of models, as well as why the decoder models have become so popular recently. The first type of model we'll discuss is the encoder-only model. This type of model takes an input sequence of text and produces a fixed length vector that represents the text. This can be one vector for the entire sequence, or it could be a sequence of vectors, one for each word in the sequence. Essentially, you can think of each vector representation as representing the meaning of the sequence. And this can be used for a lot of downstream tasks, where you want to do something depending on the meaning of the text. For example, text classification or sentiment analysis, as well as sequence tagging, where you produce a label for each word in the text, such as part of speech tagging or named entity recognition. Examples of encoder-only models are BERT, which came out in 2018 and improved the state of the art on a lot of natural language tasks, as well as some derivatives of BERT, like Roberta, Albert, DBERTA, etc. And these sequence models. So these type of models take an input sequence and generate an embedding using the encoder. Next, it produces the output sequence one token at a time using a process called autoregressive decoding. So essentially, it takes the encoded embedding as context, as well as all of the previous tokens it has generated so far, and using an intention mechanism, it generates next token. It continues this process until it finishes generating the output sequence. The most prominent example of encoder-decoder model is for machine translation, and in fact the picture here is for the original transformer called Attention is All You Need, which was published in 2017. Other examples of encoder-decoder models include T5 and BART. And machine translation is one use case of these type of models, but another one is summarization, where the output is a summary of the input text. Also, another one is image captioning, where the encoder actually receives an image instead of text, and then the decoder produces text. You can use special tags, also known as control codes, to control the decoding process. For example, in machine translation, you can use a special tag to the beginning of the output sequence to indicate the language that you want to translate to, in this case, from English to Japanese. This is useful because it allows you to use a single model to translate between many different language pairs. Another example is simplification. Maybe you would want a tag to rewrite the sentence at the 8th grade level. Decoder-only models are very similar to encoder-decoder models, but with the obvious difference that we delete the encoder, so it's just a decoder that generates text. This text generation proceeds in an autoregressive fashion similar to the encoder-decoder model, where we generate one token at a time based on the previous context. Decoder-only models are also known as language models, since they model the distribution of sequences of text, where the probability of the next token is conditioned on the sequence of previous tokens up to that point. The most famous decoder models are the GPT family of models from OpenAI, including ChatGPT. But there are many others, including PaLM by Google, Chinchilla by DeepMind, and the Llama model is the way to French. If you use it in foreign language, hopefully you now have a Can the OpenAI Whisper model do streaming ASR? My name is Bai. I'm a machine learning engineer and a PhD in natural language processing. And today I will answer this question. So if you haven't seen the Whisper model, it is a speech-to-text model. It is trained on about 100 languages on 680,000 hours of data. The model architecture is an encoder-decoder transformer model, and it comes in 5 different sizes. And it is growing in popularity recently because it is robust to noise and accents. So the question of the day is, can this model do streaming speech recognition? So first of all, what do we mean by streaming ASR? Well, automated speech recognition can come in 2 forms, batch and streaming. Batch means that the model needs to take a bunch of speech and produce a bunch of text. But streaming ASR is when the model needs to produce an output as the speaker is saying things, with a delay of not more than a few seconds. So for example, if you're listening to a live broadcast, you don't want to first record the entire broadcast and then produce the subtitles. You want it to appear at most a few seconds after it is said. And generally you expect streaming ASR to be a few percentage points lower accuracy than batch ASR because the model does not have access to all the context, only the point up until the current word. The question of how to do streaming ASR came up when I was building the voice writer. This is an AI writing assistant that works in 2 steps. In the first step, you just speak your thoughts without worrying too much about the grammar, and in the second step, the AI corrects the grammar for you. I've been finding it super helpful for writing all kinds of things, including emails, blog posts, and Slack messages. You can try it out for free in the link here, and I'll also post a link in the description of the video. Now back to the video. First of all, why is this even difficult? Why is it not so easy to use the Whisper model for streaming ASR? The issue is Whisper is trained to process input audio of 30 seconds long. If the audio is less than 30 seconds, you can pad it to be longer, so this is not too much of a problem. But what if your audio is longer than 30 seconds? There is no way to feed into Whisper anything longer than 30 seconds. So the first thing you might think of is, what if you just split it up into chunks of 30 seconds at a time and process each chunk one at a time? Well, the first problem is you might split it in the middle of the word. Like if you split it while in the middle of the word, this word will probably not be recognized correctly. The second problem is the latency will be really high. So imagine if you're processing audio, you're waiting for audio to fill up these 30 seconds, and only then will you process this entire chunk, and then the latency for the first word will be up to 30 seconds. Fortunately, there is an open source repo called Whisper Streaming that does this for you, and it turns the Whisper model into a streaming ASR system. There are instructions on how to set this up, so let's try it out. So I run this command to start a model running, it's using a Whisper small model, and then I go to this tab and go to set this up, so let's try it out. So I run this, it turns the Whisper model into a streaming ASR system. There are instructions on how to set this up, so let's try it out. So I run this command to start a model running, and I just start speaking. So you can pretty quickly see that it's picking it up, and it's pretty quick and responsive, and it even gives timestamps. So it's pretty cool demo. Now let's talk about how this works. So we start with this audio file, and what we do is we feed chunks of increasing size into Whisper. The size of these chunks is configured by the minimum chunk size parameter, which by default is 1 second. So in each iteration, we increase the size of this buffer by 1 second and feed all of it into Whisper. And this process continues until we hit our end of sentence marker, like a period or a question mark. Then we move the buffer forward and start the process again. So each piece of audio is processed by Whisper multiple times, as many times as it takes until we hit the end of the sentence. The reasons for this is Whisper is trained on sentences, so it gives the best result when the start of the audio aligns with the start of a sentence. And that's why the buffer only moves forward when the previous sentence is complete and we're beginning a new sentence. This way, Whisper never needs to start transcribing from the middle of a sentence, which would give suboptimal results. In many applications, it is useful to have some results available as soon as possible, even if they're not completely accurate. In the voice writer, I am showing the incomplete results in gray, whereas the confirmed results are in black. The difference is the gray part of the sentence is unconfirmed, so it may change as the model gets new information. But the black part is the confirmed results, and they are permanent. How this works is using an algorithm called local agreement, with n equals 2. This means that for a token to be confirmed, it needs to be generated in 2 consecutive audio buffers. Let's give an example. Let's say in the first step, the Whisper model outputs the 3 tokens if you like, and nothing is confirmed at this step. In the second step, the model produces more tokens, but only the first 2 tokens agree with the previous step, so those 2 are confirmed. In the third and the fourth steps, more tokens are generated, but at each step, it does not confirm any tokens until it is at least generated in 2 consecutive chunks. So anything in the gray part is possible to change in given new information. For example, the word view might change to video once the model hears the rest of the sentence. But anything in the black part is permanent, so even if the model wants to change it to something else after more iterations, it cannot be changed anymore. One last thing that this model does when it generates a new sentence is it feeds the previous sentence into the model as prompt tokens. So this is something that you can do in the Whisper format, is you can give a bunch of prompt tokens before you start generating. And this tends to improve the accuracy a little bit.
I'm gonna elbow someone.
Always good.
I like elbowing people.
In summary, the algorithm can be summarized in 3 basic ideas. The first idea is we feed longer and longer consecutive audio buffers into Whisper. And then we emit tokens as soon as they're confirmed by 2 iterations. And finally, we scroll forward the audio buffer whenever a sentence is completed. So it's a pretty simple algorithm that you can apply to any speech-to-text model that does not support streaming and basically turn it into a streaming model. If you like,
let's see what he has to say.
Humans don't use reinforcement learning is maybe what as I've said it. I think they do something different, which is, yeah, you experience. So reinforcement learning is a lot worse than I think the average person thinks. Reinforcement learning is terrible. It just so happens that everything that we had before is much worse. Because previously we're just imitating people, so it has all these issues. So in reinforcement learning, say you're working with, you're solving a math problem. This is very simple. You're given a math problem and you're trying to find a solution. Now in reinforcement learning, you will try out lots of things in parallel first. So you're given a problem, you try hundreds of different attempts. And these attempts can be complex, right? They can be like, oh, let me try this, let me try that, this didn't work, that didn't work, etc. And then maybe you get an answer. And now you check the back of the book and you see, okay, the correct answer is this. And then you can see that, okay, this one, and that one got the correct answer, but these other 97 of them didn't. So literally what reinforcement learning does is it goes to the ones that worked really well, and every single thing you did along the way, every single token gets upweighted of like, do more of this. The problem with that is, I mean, people will say that your estimator has high variance, but I mean, it's just noisy. It's noisy. So basically, it kind of almost assumes that every single little piece of the solution that you made that arrived at the right answer was the correct thing to do, which is not true. Like you may have gone down the wrong alleys until you arrived at the right solution. Every single one of those incorrect things you did, as long as you got to the correct solution, will be upweighted as do more of this. It's terrible. Yeah. It's noise. You've done all this work only to find a single, at the end you get a single number of like, oh, you did correct. And based on that, you weigh that entire trajectory as like upweight or downweight. And so the way I like to put it is you're sucking supervision through a straw because you've done all this work that could be a minute of rollout, and you're like sucking the bits of supervision of the final reward signal through a straw, and you're like putting it, you're basically like yeah, you're broadcasting that across the entire trajectory and using that to upweight or downweight that trajectory. It's stupid and crazy. A human would never do this. Number one, a human would never do hundreds of rollouts. Right? Number two, when a person sort of finds a solution, they will have a pretty complicated process of review of like, okay, I think these parts that I did well, these parts I did not do that well. I should probably do this or that. And they think through things. There's nothing in current LLMs that does this. There's no equivalent of it. But I do see papers popping out that are trying to do this because it's obvious to everyone in the field.
Yeah.
So I kind of see as like the first imitation learning actually, by the way, was extremely surprising and miraculous and amazing that we can fine-tune by imitation in humans. And that was incredible. Because in the beginning, all we had was base models. Base models are autocomplete. And it wasn't obvious to me at the time, and I had to learn this, and the paper that like blew my mind was Instruct GPT, because it pointed out that, hey, you can take the pre-trained model, which is autocomplete, and if you just fine-tune it on text that looks like conversations, the model will very rapidly adapt to become very conversational, and it keeps all the knowledge from pre-training. And this blew my mind because I didn't understand that it's just like stylistically can adjust so quickly and become an assistant to a user through just a few loops of fine-tuning on that kind of data. It was very miraculous to me that worked. So incredible, and that was like 3 years of work.
Okay. I'm gonna take a break. Probably not. I think I'm done for the day. I'm gonna tomorrow. I'm gonna do that. Maybe I'll like learn some statistics, but I'm not in the learning mood right now.
This video is sponsored by KiwiCo. More on them later. Also, I've written a whole new book on AI. You can learn more about the book at the end of this video. When I first learned machine learning, these 3 books were incredibly helpful, but they're also all wrong. Each book has a version of the same plot, a core tenet of machine learning theory and practice. The x-axis shows the size of a learning model, and the y-axis shows the model's performance, measured using some type of error metric. From here we plot 2 curves. The first curve shows the model's performance on its training data. As our model becomes larger, it's able to learn more complex patterns, better fit its training data, and bring down its error. Of course, what we really care about here is how well our model will perform on examples outside of its training set. Our second curve shows the same error metric, but measured on a test set that the model hasn't seen before. Again and again, in every book, the test set error curve has the same U shape. Our testing set error starts high for smaller models, comes down to a nice minimum for some medium-sized model, and shoots back up as the size of our model continues to grow. The shooting back up part of the testing curve is due to the model overfitting the data. Many authors demonstrate the overfitting phenomenon using polynomial curve fitting. If we take a set of data points, for example this set of parabola-shaped points, and set aside half of our data for testing, and fit a first-order polynomial, which is just a line, our curve fit will be poor. We can measure just how bad our fit is by taking the differences between our fit line and our training points. Squaring and averaging these errors together, we get the mean squared error of our linear model on our training set. We can repeat this process on our test set points to compute our test set error. Both our training and testing errors are relatively high because our simple linear model is not powerful enough to fit our parabola.
I'm gonna have to like find another way to do it. Fuck it, tomorrow. I need to work on that. I got like so much shit to work on. I'm done.